Thank you for coming to the talk. As Marco mentioned, it's the last one of the day. We can all go to party after this. So hopefully I won't keep you any longer past the 5:30 deadline. Just as a quick show of hands, how many people have heard of Elasticsearch at all? Okay, about half a dozen. And how many need to solve a full text search problem for their product? A lot more. Good. So who am I? And decided to use Elasticsearch to answer that question. We'll talk about what all that means in a little bit. But I've worked on projects such as PHP for over 10 years. I did PHP GTK and Smarty, whether you want to hate me or love me for that. Although I haven't worked on it in a long time. And I also started and sort of ran the project to do Unicode and internationalization support in PHP, which kind of got tabled for now. I like coding, obviously. I like beer, both drinking and brewing beer, and photography and a bunch of other stuff that didn't fit on the slide. So if any of that interests you, come talk to me at the party. We can discuss any of that stuff. I'm @A on Twitter, which is awesome and horrible at the same time because my reply stream is useless. If you want to see what it looks like, ask me. I'll show you. It's people tweeting nonsensical stuff or saying, I'm at a bar. It gets worse. And my email is there. All these slides will be up both on my site and I think on PHP UK site later, so you don't need to write it down right now. So what is Elasticsearch? It's a full-text search engine that has been designed for the NoSQL generation, is sort of my tagline for it. The guy who started the project, Shay Bannon, he worked with Lucene a lot in the past, and he did another search engine called Compass on top of that a few years ago. But when he started Elasticsearch, he wanted to write a product that was sort of optimized for the new movements that have been happening in the last couple of years, such as cloud, JSON, and all the things related to that. And he believes that the product should be domain-driven, meaning that the product should speak your domain language, not the other way around. So you don't have to adapt your data to fit the search engine. Your search engine should adapt to fit your data. He also wanted to make it distributed out of the box and as easy to set up as possible. And make it RESTful to be able to work over HTTP and thus interface with any number of libraries or products that use HTTP. It is also Hitchhiker's Guide to the Galaxy. I'll show you in a second what it is, but really there is text of Hitchhiker's Guide to the Galaxy in the source code. The document model that Elasticsearch uses is basically a document-oriented search engine with I think almost complete asset support. So if you index a document, you can be guaranteed that it won't be lost. If things are configured properly, it will be consistent. So while a document is being indexed, it's not going to be read partially by another process and so on. It is JSON-based, as I mentioned. And like a lot of other products that JSON-based, it's schema-free. So you are completely free to use whatever schema you want for your documents and even change the schema later if you see fit, if you need that option. The engine underneath Elasticsearch is based on Lucene. Basically, every shard, which we'll talk about what a shard is a completely separate Lucene index. And because it is Lucene-based, it brings with it a lot of the Lucene settings and options that it has. Not quite all of them. I think Lucene still has some things that he hadn't implemented interface for, but there's definitely a lot of similarities there. It also has what's called multi-tenancy, so you can have the same node, same machine running multiple indexes, and within each index you have different types of documents. Sort of like a database with databases and tables and so on, but slightly different. And like I mentioned, it is distributed out of the box. It has very efficient asynchronous transport protocol that the nodes talk between each other. And there's automatic node discovery and all kinds of cool stuff that you will see. Just a nomenclature before we go on. So the index is a collection of documents of one or more types. So sort of like a database in the normal RDBMSs. You can search each index either for a specific type of document or for multiple types that it contains. And it allows you to sort of be very free about how you model your data. Some people use just one index and put all their data in there. Some do one index per day if they're indexing log files, for example. And it's very easy for them to sort of manage that, delete that index, create a new one, and so on. And documents are schema-free. The only required field, or even not required, is _ID, which is the sort of unique key that you need to provide for the document. If you don't provide it, it will be auto-generated for you. So you don't even need to supply that. And then the node, of course, is a machine that's running an instance of Elasticsearch and providing the indexing and search capabilities. So 3 easy steps to search success, right? What we basically need to do is, step 1 is index stuff. And because it has an HTTP protocol, everybody can see this? Is that good? OK. We can use good old regular curl to interact with from command line even, which is how I like to test stuff. So to index a document, let's say we're running a localhost port 9200 is its default port that it runs on. We just say curl, and I explicitly say that it's a post request here, but if you supply the data as a request body, curl kind of assumes it's a post. And then you just give it a JSON document. In this case, we want to index, let's say, a list of speakers for the conference. So /conf is the name of my index that I'm putting stuff into. And /speaker, after that, is the type of this document. It's a speaker document that's in the conf index. And /1 is the ID, the unique ID I talked about. So we just index this document. And what we get back is another JSON document that describes the response of Elasticsearch. In this case, it says, OK is true, which means everything went fine. And it also returns what index the document went into, what the type of the document was, and the ID that you provided, sort of the confirmation. Second step that we want to do is search. And using curl again for that, we basically say curl localhost 9200, which index, which document type, so /conf /speaker. And then we give it an action, which is _search. And in this case, we're just putting the query straight in the URL, and there's a query string, so we want to search for beer. And what comes back is the response, also a JSON document, and we'll sort of go through some of the fields to show what they are. So it'll tell us the total number of hits. In this case, it's just one. We just created this index, and there's only one document in it. This field will be different if you, for example, do some sort of paging. If you say limit to 20 documents, when this comes back, it'll actually show how many total documents match. So you don't need to do another query to find that out. That's returned automatically. There's the index where the document came from. And this is important because you can search across indices, as you'll see. And the type of the document, the ID, of course, and then the hit score, which if you want to use that for whatever application in your client, you can do so. And it also gives you back the original source that you stored, which can be handy if you don't need to go back to another data store to retrieve what this document was about and so on. You can basically just use these fields directly out of the response. And another interesting thing is also it tells you the execution time in milliseconds. So this is 3 milliseconds, which is, for one document, it's pretty fast. But as you'll see, it's fast across millions and millions of documents. The third step is profit. That's up to you, how you use Elasticsearch in your quest to conquer the world. Everybody with me so far? OK. So I like doing demos during presentations. So in this case, we'll just go back to my terminal. Is this big enough for people? And I tried not to put stuff on the bottom here. I limited my terminal because I know people can't see behind the heads necessarily. But what I have here is I have a virtual machine that I'm running with with an Elasticsearch. It's Java-based, of course. Then I did some sample documents. So I want to create exactly that index that I talked about, the conference one, with speakers. So I have 3 speakers here. That's me. So let's go index me, and I put some different things in there, like Twitter stuff and height and whatever. So we just go to virtual host, and we execute this, and it gives us back that document. And you notice that I didn't create an index, because it assumes you want to, if there's nothing, if it doesn't know about that index, but you tell it to index this document, it'll automatically create the index, automatically figure out some other things, so you can just get up and going. So let's index Derek's record. His talk is about Xdebug, and he likes, instead of beer, he likes wine and PHP, and he is a bit taller than me, about 1 centimeter taller. He's a tall guy. We'll index that as well. And then Ian, he gave a talk about zero-conf, which is an awesome talk, by the way. I think he likes beer too, and I think he likes linguistics, right? Okay, good guess. I don't know how tall you are. I'll just put 175, because that's, who cares? This is just a demonstration. And then, so I have this conference index, and I created those 3 records or documents for the speakers, but I want to index the talks as well. And in this case, I'll just say, oh, it's a different type of document. It's a talk document instead of a speaker document, but it still goes in the same index. And the ID is, of course, unique to index type combination. You can reuse the same ID for this. So I'm just going to index these 3 talks, and need to copy this one as well. This is the first time I'm giving this talk, so if things go wrong, please be gentle. OK, so we index this. Let's see what our status of the index is. Conf index status. Pretty true. We want to actually read this JSON. So it comes back with a whole bunch of stuff about our index. Things like here's the, well, highlighting doesn't really work here, but you'll see that it has a bunch of shards, number of documents that are in the index. Max doc is equal to number of arcs because I haven't deleted any. And it only has 1 shard here by default, which is fine. So now that we have these documents, let's do some searches. So wow, this is completely horrible. So as the first request, let's just search for Derek. So boom, it came back, and it did find Derek. And you notice we didn't say what field to search on at all. We just gave it a query string. And what it does by default is that when you give it a document, it puts all the text fields that it knows about into another field called _all. And that's what it uses to search against by default, so you don't have to even specify which field. Let's search for photography, which was actually in the tags rather than in the name or anything else. So here you see it went through and found 2 records for Derek and me, because we both like photography. You can use AND operator. You can say photography and beer, as any good search engine should let you do. Well, in that case, that'll find me. So you can see that works fine. But if you want to specify a field to search against, you can do it with a syntax that says name, which is the name of the field, colon, and the what you're searching for. So if we go and do that, boom, OK, it found Ian. Now you notice that we were executing all these against the /conf/speaker, so conf index and speakers. Now let's search for another type. So we're going to search for talks now. We're going to search for talks that have PHP in the description. OK, so it comes back and says zero-conf is the answer. There's something about PHP there, and the other one has PHP as the very first word. OK, good enough. What we can actually do is search across types. If you look here, we're doing speaker, comma, talk, which means we're going to search for both document types and see which ones will contain PHP. So once we do that, if you scroll up, that will say hits 3. And the first hit is actually, it says type speaker, because Derek had PHP in his tags. And the other 2 have the PHP in a description, of course. We can also limit the fields that are returned. If we say we just want the name and the likes, and I intentionally name the field so that name is common between the talk and the speaker. So if we do that, then it just returns the name and the likes. And as you see, the field which is not present, if it's not present in the document, is just returned as null. Like for the talks, for example, it says the name of the talk, but we don't have any likes for, obviously, for talk type. So this is just a quick intro into index and searching. So let's go back to the slides. Now, the big part of Elasticsearch, as I mentioned, is the distributed model. And it gives you a couple of things. It gives you performance because you can distribute your indexing and your searching across the nodes. It also gives you resiliency or high availability. If it's designed in such a way that if one node fails, the other nodes will automatically sort of pick up the load, and you can add documents on the fly, and you don't need to worry about which shards go where, which replicas. It'll rebalance things transparently. So what is a shard? A shard is a portion of the document space. Each one is a separate Lucian index, as I mentioned before, and you can have many per index settings. You can tune certain indices to be optimized for writing and others for reading, and any number of other things. And the documents are sharded by the ID values. Since those are never change, that's fine. And when you ask Elasticsearch to index a document to figure out which shard it should go to, sort of behind the scenes, but if you do want a certain group of documents to end up on the same node deterministically, you can provide another key which says, well, basically keep all of these documents on this one node, so in case you're indexing a certain collection of documents together, which will be a little better for performance because it doesn't need to go and fetch them from another node and aggregate the results together. It also has zero-conf discovery, both in the cloud and on normal servers. It uses multicast and unicast discovery, IP-based discovery via the Zen module, so-called. So on your own network, you can just bring up another node, and it'll, if it's within the same IP range or IP subnet, it'll figure out that it's running. Or in the cloud, which is currently EC2 only, it'll use the EC2 API to see that a new node has joined the cluster, and it'll automatically start distributing, indexing, and search operations to it. In any cluster, and you can have multiple clusters on your network, there's a master node, which the only sort of difference between a normal node and a master node is that master node is responsible for maintaining the cluster state, so that it knows which shards are, which node has primary shards, which has the copies of those shards, and which nodes are in the cluster. If a new node joins the cluster, it will let other nodes know about the new node. And it also reassigns the shards between nodes if the nodes leave or join the cluster. Now, you can issue requests to any node in the cluster. It will be automatically routed. Each one can basically serve as the primary point of serving a request. And the query is handled via the scatter-gather mechanism. So if you issued a query and it has like 4 shards it needs to look for in the document, it'll ask the other nodes to find the document in their shards that are responsible for, get the results back, rescore them if it needs to, and then return the results to you. Now, each shard can have 1 or more replicas, and this is good for both performance and for resiliency. unlike number of shards per index, the number of replicas can be updated after you create the index. So you can create index with 0 replicas, which in elasticsearch terminology means 1, because there's always a primary shard. You can index a bunch of data into it, and then you can update and say, okay, I want 2 replicas for it now, and it'll just, if you have multiple nodes, it'll create the replicas on the other nodes automatically. If you want to index a bunch of documents without creating replicas right away, that can be done. And the replicas, of course, can be used for querying in parallel, because each one, as you remember, is a separate server that knows how to handle the requests. So how does a shard allocation work? So suppose you start with a single node. And you say put. You use put to create an index as a HTTP verb. Put/person, and then you give it the index settings that you want this index to have. So in this case, we want this index to have 2 shards and 1 replica, which actually means 2, right? So it'll go ahead and create those 2 shards on the node. I color them differently just so we can distinguish them better. Now, we start the second node. And what will happen is that the first node will detect that it's the master node, because it's the only one, detect that the other one joined the cluster, and it'll copy the replicas. When you created the first node, both of those replicas for each shard were on the first node. And when the second one joins the cluster, it migrates those replica shards to it. Now, if you start 2 more nodes, what's going to happen is that the master is going to have to reassign the shards, because there are 2 available nodes, and we have 2 shards times 2 replicas. There's 4 different shards. So what it's going to do is take, so this node is going to have shard 1 primary. This is shard 2 primary. This is shard 1, replica of shard 1. This is replica of shard 2. So now, even if we add new machines to the network, it's not going to do anything, because it already sort of redistributed all shards. But any of these machines you can query for data, and it'll know how to do it. So let's index some data. If you say put person info type and then document 1, it's going to hash to shard 1, for example. And then when you, as soon as it's hashed to shard 1, it's going to be replicated to the other node. So right away you have a copy of the data they can use for querying, or if the node 1 goes down, then that shard is still available on node 3. And say index second document, hash to shard 2, and replicate it to node 4. Now when we issue a query, let's say we just ask node 1 for that. We say get/person _ search, and we just want to search for name Thomas, let's say. What the node 1 is going to do is it knows, is there 2 shards, it knows which nodes are responsible for those shards. So it's going to query the shard that it owns, and then the shard that node 2 owns, collect all the hits, document hits from those, merge them, and then return them back to you. And any of these nodes can do the same operation. I guess you can think of Elasticsearch as a transactional system, because, as I mentioned, it has per document consistency. If you can, it treats the documents as a whole. You can't go and update just one field in a document. You need to supply the complete JSON. And but you don't need to do any sort of like commit or flush. As soon as you index a document, it'll be handled automatically. There's a right behind transaction log that it keeps in case of crashes. There's a periodic refresh. By default, I think it's 1 second, so you don't need to issue even an index refresh. If you index something, within 1 second, it'll be available for searches. And you can also control write consistency. If you went to Lorenzo's talk, he mentioned that number of write replicas and how that's important for consistency. You can pass a separate pass a parameter during indexing that says, well, I only care about 1, or I want a quorum, or all. basically success is dependent on how many replicas you want the document to go to. Like I said, there's a 1-second refresh rate by default, but there's also a refresh API in case you want to control that manually. You want to index some documents and then issue a refresh and have it available for search. One thing to understand is that the index data that it maintains is considered transient. You can store it in a local file system or in JVM heap or in a memory or file system and memory combination, but if you restart that node, that data will be gone. So if you want persistent storage, it requires what Elasticsearch calls a gateway. Now, this gateway is used to store the cluster metadata. So basically which shards are where, what the names of indices are, index settings, and so on, and the actual index data itself. It uses an asynchronous translog-based write strategy, so for performance reasons. And the gateway allows you to do a full recovery if something goes wrong and your cluster crashes, and then you need to do a full restart. It can recover the actual index data from gateway. And the supported gateways, which depending on your needs can be, you can choose one or the other, are local is the default in the new version of Elasticsearch, where it uses the node's local index data to recover from rather than fetching from some other source. In that case, your index has to be stored on disk. It can't be stored in memory because that's volatile, obviously. Or you can use a shared file system such as NFS or whatever else you can you want to use. Also supports Hadoop or Hadoop file system actually, and S3, Amazon S3. So you can keep your index data. You set the gateway to S3, and it will do periodic snapshots to via the S3 API, which is pretty cheap actually. So mapping is another important concept, and this is basically your description of your schema, not in the sense that it's rigid, but it describes the document structure and types to the search engine so that it can index different fields in different ways, or give it different boost levels and so on. By default, you don't even need provided mapping. Like you saw in the examples, we just index a document, and Elasticsearch will like magically figure out, well, I see a string, so I probably should index it as this type and do a full text search on it. Okay, this is a number, so I should do a different index so I can provide numeric range searches, for example, and so on. You can provide explicit mapping if you want to customize some of those defaults, and it's generally a good idea. And if you provide a mapping or use a default one, if you later try to update, if the mapping already exists and you want to like add a field, that's fine. It'll just modify the mapping to add a field. But if you want to change type or do some other things, you may run into merge conflicts, and there are a couple of ways of resolving those that the documentation describes. And the mapping has some important meta fields. One is that underscore source, which you saw when you do a search. It returns back the source of the original document. And it's optional. You may say, don't store the source when indexing the document. All I want is, ID, maybe a couple of fields. I don't care about the full document. The other one is, and the source, by the way, can be, you can enable a setting that uses LZW compression, so you kind of save on the index space that way. Underscore all is that synthesized field where it takes all the fields in a document and merges them basically into one. Lets you do things just like searching across fields, and it also respects different fields boost levels. So if, let's say one field is twice as important as the other, it'll handle that properly. And there's also, among others, is the underscore boost. So that is basically indicates a field in the actual document which provides the boost level. So you can have per document boost that says, okay, this document is very important, this one's not so much. And you don't have to do it in the query itself or in the indexing, I mean, you can just have it in your database or in the document. The types that you can use for the mappings are pretty standard. You have integer, long, string, Boolean. There's also null, but there are a couple of more complex ones like array, native support for arrays and objects. And for arrays, you don't even need to say it's an array. If you can just indicate the type of that the array contains. Like if it's a array of strings like tags, you can just say it's type string. It'll automatically figure out an array and let you do searches on that. And object is good for nested JSON objects. So you'd have if you have a person record, you can have a name split into first and last fields and map those separately if you need to. So here's a sample mapping using the document that the person document that we saw. So we have user, title, tags, post date, and priority. And here's how you describe the mapping by saying it's for the post type of document. I know this is a low, but hopefully you can look at this slide later. I'll just quickly say what they are. And then the properties, which is what we're describing, is we're saying user is type string, but we don't want to analyze it. We don't want to do full text searches in it. We just want to sort of use it as a whole, as a keyword. And I think I messed up. This should be de-indented one level. Message is type string, and we want to boost it 50% so that it results, if it matches on message, it will have higher score. The score for the document will be higher. Tags is just type string. Even though it's an array, it'll automatically figure that out. And we say we don't want to include it in all, in the underscore all field. Post date is type date, and you can do custom date formats with a Java-based sort of date formatting. But let's say we don't want to store this in the index. So if we don't have an underscore all field, and we say store no, that field won't come back at all. It's only used for indexing. It's not going to be returned as part of the result. And let's say priority is just type integer. So mappings are sort of a very flexible way to describe your indexing and querying needs. This is slightly different, but sort of feeds into the mapping. There's a concept of analyzers in Elasticsearch, which is how it breaks down the text in the documents and how it normalizes the fields during indexing and also during query time. And an analyzer is basically a tokenizer that knows how to tokenize a field and 0 more token filters to transform that in some way. So there's a standard analyzer that is applied to sort of every field, like title, description, whatever, and it's a standard tokenizer which has a couple of its settings, and a standard token filter, and a lowercase, and a stop token filter. So by default, it'll lowercase all the text on indexing and during query time, so you don't have to care about case. And it'll also, the stop token filter will filter out things like articles and prepositions and so on automatically. But you can customize this if you want. You can customize tokenizers and filters and do a number of things like, well, my max word length is 20. I don't want to worry about that, or provide custom list of stop words and a number of things. One thing that I found useful to customize is both ASCII folding and stemming. So ASCII folding, for example, if you're using European languages, you want to care about accents. You sort of want to fold those into ASCII letters. So here's how you customize an index. This is in the YAML format. That's what it uses for config file. Index, analysis, analyzer, and then the bold one, I just call it ulang for European languages. I have a custom analyzer. I still have a standard tokenizer. And then I just append a couple more filters here to the standard ones of lowercase and stop. I say I want to do ASCII folding and Porter stemming to stem words, so that if I search for fish, it'll also find fishing and things like that. And the new release of Elasticsearch, it actually supports snowball stammer also, which is of higher quality than Porter stammer. And then in your mapping, you just say type string and give it the analyzer. And this analyzer will be used during indexing and to analyze the query at query time. You can specify separate analyzers for both if you want by default. This is sort of most common case. Everybody good so far? Yeah.
You put multiple analyzers on one field?
No. You can't put multiple analyzers on this for the same field. But you can sometimes combine properties of different analyzers into the same if you want to mess with the filters and so on. Sort of the API, I'm not going to go into all of it. I'm just going to sort of run through it because it's fairly extensive. But sort of some conventions is you can append pretty equals true to any URL, and it will give you back prettified JSON with indented, sort of like human readable almost. Boolean values, false, 0, or off is false. Everything else is true. And if you want JSON-P support, just provide a callback argument. So that's all built in. And the general API structure is you have host, port, then an optional index, optional type, because you can search across multiple indices and multiple types, as you saw. And then you have an action, which is like underscore search, and a couple other things, or an ID for indexing documents. So as an example, you can do status, underscore status, and that'll give you the status of your cluster, how many indexes it has, and so on. Or you can get a status for a specific index, /index/action. Posting we already saw. If you do get on the same, you'll just get back that document that you just indexed. You can do index type search. Here's another type. Or you can search across types, as we saw. You can search across indexes also, if you just do same convention of separating them by comma, which is pretty useful in certain cases. Or if you just do underscore search, it will search all the indices, all the types. There's also underscore cluster API. To get some metadata about the cluster, you can ask it for cluster health, which will tell you red, yellow, or green. And green means like all the shards have been allocated properly, both primary and secondary. Yellow is just basically couldn't allocate some shards, but it's still running, but it's just not going to be resilient in case of failure. Some node stats and node info if you want for things like how much memory currently has, what the CPU load is, and all kinds of stuff like that. The core API allows you to do a bunch of things. So index we already saw, that's for indexing document. There's also a bulk indexing option, so you can feed it a chunk of commands. Let's say index, 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 delete, create, whatever, and feed it to like 200 documents at a time. And that's way more efficient for indexing a bunch of things than just doing it one by one. Delete, pretty obvious. You can just delete a document, and you can also delete by query if you want to delete a certain sub-range of documents. Whatever queries you can use for searching, you can use for deletion, which is pretty cool. Get is just retrieving one specific document, as we saw. Count is useful when you just want to get a count of the documents that match without doing any retrieval, because in the case of retrieval, it actually sometimes needs to go disk and retrieve like the source that you gave it, maybe parse it, and so on. You just want the count, use count. And then a pretty extensive search API, obviously. And sort of the portions of the search that are useful most of the time, I think, is like query, which is the actual query you're searching for, the from size for paging through the result set, sorting on one field or more fields if necessary, highlighting, which is pretty cool if you want to highlight what matched in the search results, retrieve selective fields, like you saw, we only retrieve name and likes and so on, and a few other things that are really cool. Then there's the API for working with indices. So you can obviously create an index with certain parameters. You can delete an index. You can also open and close an index. So if you know, for example, that you're not going to be working with a certain index for a while, but you still want to keep it around, you can close it. And you obviously won't be able to query it, but also consume way less memory and just no processing time at all. And when you do, when you are ready to work with it, you can open it and it'll do the same thing that happens during cluster restart, retrieve it from gateway or whatever, and bring it into ready state. You can get, put, delete the mappings for your documents. And if you delete the mapping, it actually wipe out those documents, by the way. The refresh I already mentioned, if you want to manually refresh the index to make the documents available for search. There's also optimize. When you delete, if you do a lot of document deletions and so on, there may be some spaces left by them. So if you want to optimize the index storage, that's one way to do it. Query. Why is this query? I think that's a mistake on the slide. Snapshot. By default, it snapshots to gateway to the persistent storage every 5 seconds or something like that. Or you can ask it manually to do a snapshot if you want to do it from a cron job or something, if that's what you need. Update settings is how you change the number of replicas per index. There's also analyze, which it tells you how it breaks down uses the analyzers to break down the text, which I can actually show you. It's pretty cool. So here I have a text going fishing, and I'm going to use that ulang analyzer that I showed an example of. So if you do that, it comes back with it says 2 tokens, and a token is a go and fish because it did stemming and lower casing and all that other stuff, and it has some other what type of token it is, what position it's in, and so on. So you can use to debug your analyzers and see how they're working. We can do different ones. We can just use, let's say, white space. And then it will just tokenize on white space and not do all that other stuff. There's also cluster API. What was that one? Oh, yeah, status. I already talked about that. So there's a cluster API for health, state. You can shut down nodes programmatically via API if you need to. And there's a pretty extensive query domain language that you use in the query itself. So terms is just for searching for keywords or list of keywords. Range is for obviously a range of numbers. Prefix is searching for words that start with a certain prefix. There's a Boolean query that you can say, okay, this must appear, this must not appear, and you can use whatever subqueries you want in that. Fuzzy, using Levenstein algorithm, you can do sort of fuzzy searching to find approximately matching words. Wildcard, obviously. And then this query string, which is what it does by default when you say q equals in the URL. And it has a bunch of its own settings, like default operator, which is or by default, but you can set it to and. So if you give it 2 words, it will use and operator on them automatically. You can change the analyzer to do at query time. Phrase swap is pretty cool if you search for phrases. Well, usually it means, if you search for 2-word phrases, they have to be next to each other. If you do set phrase swap to 1, you can put, even if they're separated by 1 word, it'll find it. And a bunch of others. And I'll just show you quickly. So let's see, prefix. And here I'm starting to send queries as JSON documents in the post body because it allows for a lot more query types than the URL. So here we want to find everything that starts with PH, and obviously photography and PHP matched. And then let's say we're searching for linguistics, but we don't know how to spell it with, say, linguistics. And we're doing a fuzzy search with a prefix length 2, meaning that the first 2 letters have to match still, because otherwise Levenstein goes kind of crazy. Oops, it found Ian, because he likes linguistics, apparently. Here's a Boolean query. We're saying must term likes coding, and must not range height less than 188. So we want to find tall coders. And that's Derek, because he's the only one that's 188 or higher. Here's the query string one, and it's sort of weird syntax because you say query, then query string, then a query field in that. And there we do things like find PHP, but that matches PHP, but not proxy. And we only want to search in description. And so that works and finds the zero-MQ talk because it doesn't mention proxy. And there's phrase swap. So we want to search for a PHP extension. but in case something else comes between those, it's fine. And that's true because it says PHP ZMQ extension. Highlighting, which I already mentioned. So I searched for varnish in the query, and I want to highlight the name and description fields if that appears there. So when it comes back, it breaks them down to these fragments, which you probably saw from other search engines, but it puts em/em around varnish here and here. And you can customize what those tags are and do a number of other things. So filters they share some similar features with queries. There are term filters, range filters, and so on, but why would you use a filter versus a query? Well, they're way faster than queries, and they're cached, unlike queries. Sort of depends on the filter, how the cache is used. But if you run different queries against the same filter, it will reuse that cache, so it's even faster then. And the reason it's faster, it doesn't need to do any scoring on the filters, and most of the time you don't need scoring for things like numeric range queries, querying for numeric range and so on, or for whether something exists or missing. And some of the useful ones are listed here. So you can, for example, search for some sort of text and then filter only, like find, we could have rewritten that Boolean query as searching for, let's say, some sort of text and then filtering by the height instead of doing that Boolean must not, which would be faster. Facets give you aggregated data based on the search request. Things like histograms and statistical and terms. Like, for example, if we wanted to find what are the most common terms that are, we can do something like this where we say match all documents, and then facet is on the field likes. Tell us what the most frequent terms are. And if you do that, whoop, that's not the right one. It comes back with something like that where it has a likes facet in addition to search results, which are up here, by the way, because we say match all, it returned all documents there. But the most common one is coding, and the next one comes photography, and so on. So you can sort of display those at the same time. Or we could do, oops, statistical facet on the height. And that comes back and says min 175, max 188, variance and standard deviation, all that cool stuff if you want to. So I have 10 minutes or maybe 9 minutes now. There's also GeoSearch. You can set the field type to be geopoint, and then you can do filters on geodistance, if it fits in the bounding box or polygon, which is actually really cool. Let's see, do I have time for the EC2 stuff? Yeah, I was going to show you how how cool it is to have totally distributed search engine. So I have EC2. I have 3 servers running. One's the client, 2 are the servers, and it's really cool to do this with EC2 for like demos and stuff. So I'm just going to SSH into that. And what I have here is I suck down 1 million tweets from Twitter and indexed them, certain fields from them for searching. So right now, if I do cluster state, oh no, not state. So if I do cluster state, it's going to say I only have 1 node. At the very top, it says nodes, name, and it gives funny names to nodes. And whatever data is after that, but I only have 1 node. So all the shards, I specified 4 shards for this index with 1 replica, so basically 2 replicas. But since there's only 1 node, they're all on the same node. And so let's do query. I wrote this little Python script. Sorry, not PHP. Python has this multi-processing module, which makes it way easier to like fork out a bunch of processes and then have them do work. So I have 20 processes, and I want to query this index, a 1 million document index, for 10 seconds, which hopefully, oh no. Oh yeah, there it goes. So I went through and those 20 workers did about 209 queries per second against this index. Well, let's say this is only 1 node. I'm going to, the node is actually up, but I'm going to just start elasticsearch on it. I specified that the data lives in, so this configuration file says data in data elasticsearch, some log files. There's the cluster name, some of my API keys for Amazon. Don't write them down, please. And then the discovery, so how it's going to discover the nodes. This is the EC2 type of discovery, and it's using the DB group and so on. Anyway, there's nothing in data, right? So I'm going to start up Elasticsearch here. And here I'm going to query for cluster health. Watch HTTP localhost cluster health. So, oops, curl, forgot curl. Oh, not a localhost, the ES1. Anyway, pretty, that would help. So here's the health that says it's yellow, which means it wasn't able to allocate some shards. There's only one node and some other data there. So if we start the Elasticsearch on the second one, it says starting. We come back here, and pretty soon it has number of nodes 2. And it says unassigned shards, initializing shards, and then when it's copied the data over, it's going to say active, how many active shards are. Boom, there's 6 active shards now. So now we have a replica or a $1 million index pretty quickly, and we can search against both, and now we have better reliability and so on. So I can actually query against both if I say yes to 99. Let's do the same. And if I had more time, I would run atop and let you see that it's going to both actually and so on. Whoa. Oh, I'm also using thrift here, so that may be, this would have maybe a bug in the thrift thing instead of HTTP. But let's go back here. So the interfaces I already mentioned, REST, there's a memcached module which lets you sort of use memcached semantics for getting and setting data and so on. There's obviously Java and Groovy interfaces because it's all Java-based. You can write a Java module that's probably higher performance than doing external HTTP clients. And then a number of language clients via REST and Thrift. There's one for Python called PyES, PHP. There are the standalone ones, and there's Symfony has a module for Elasticsearch now. Ruby, Perl, and so on. Flume sync implementation. I mean, people use Flume, no Flume. It's like Facebook Spread, or whatever it's called. Not Spread. Huh? Scribe, but like I think better. Just a system to aggregate data and collect it. So this Elastica is sort of, I think, the better of the PHP clients. API naming is consistent with Zen framework, so if you use that, it'll kind of help you. You can extend it for new filters, facets, and so on, but it's kind of still under development. An example is pretty easy. I don't use Zen framework, so I'm assuming that's what the naming conventions are, but like Elastica client, Elastica index, we'll create index, we'll create the document, we'll add the document, and then we construct a query, run a query, and so on. It's pretty easy. So one question comes up with how do you get your data in Elasticsearch? Because that's usually not your primary data store. Well, you either write an agent that sits in somewhere and you send actions to it saying like index this document, and so you don't, because you usually don't want to do this synchronously, you want to do it asynchronously. And you can use Gearman or message queues like zero-conf for that or whatever else to write an agent that will index data or delete data from Elasticsearch. Or it has support for what we call rivers, which is really cool. It's basically a built-in way for Elasticsearch to suck data from somewhere. And it has support for CouchDB, RabbitMQ, Twitter right now. So you can basically from command line say curl, and there's underscore river, and you configure it for your CouchDB, and it'll automatically start syncing data from Couch if you want. Or RabbitMQ, which lets you use a lot of other stuff. 10 more features, which I haven't mentioned. Well, let's do a couple. There's load balancing nodes. So there's a setting you can turn on and off per node that says store data on it or not. So you can have nodes that act purely as routers, like load balancers. You can have 1 or 2 nodes like that, and all the data nodes, and the other one will just store data and respond to that. parent-child docs, you can say, well, this document, this is the parent one for it. So it lets you do some sort of hierarchical modeling. And then you can, when you do a search, you can say, okay, for this document, give me all the top children, or for this document, give me its parent. So it'll automatically sort of return stuff to you that way. There's scripting support. You can do things like do dynamic fields based on other ones. You can script your scores, do a whole number of other things. I have 1 minute left. Who wants to stay for 2 more minutes?
What about plugin?
Oh, yes. It has, so it has a plugin architecture at its core, and that's how Thrift Transport is implemented, for example. This is how Cloud, Amazon Web Services is implemented. So if you know the API for Elasticsearch, you can write a plugin and do a whole number of things that you can probably plug into everything. Percolation is really cool. It's sort of inverse to search. So usually you have a query that you run against the documents, and it gives you back the result. In this case, you store your queries in Elasticsearch, run a document, and it gives you back which query would match it, which you can use for a whole number of things, I think. Like filters, like doing like email filters and a bunch of other stuff. So here are some references for it. It's on GitHub. It's an open source project. There's a Google group for it. I misspelled the Elasticsearch on the IRC. I need to fix that. And I'll put the slides at this URL, hopefully today, maybe tomorrow when I have a better Wi-Fi connection. And that's it. If you have questions, please come find me after this, and we'll have a more informal talk. Or can we have questions now? Yeah. OK, let's do questions now. Yes?
Sorry, how is the consistency? Sorry, how is the consistency handled by the client or the
No,
Elasticsearch?
by Elasticsearch.
Okay, so you just get. So how does it work? Briefly.
Consistency in what sense? Like if you give it index a document, will it be?
Well, you mentioned earlier just that the consistency is available, but you didn't say how it's achieved, whether by the client. So you mentioned that it's either form or.
Oh, write consistency? Like if when you store a document? Yeah. Well, when you store it and you can give it an option saying return as soon as it's stored in one replica, or make sure that it's stored on quorum, which is usually number of nodes divided by 2 plus 1, or when all the replicas have stored it.
I work with a place where we just implemented Solar, and one of the things we found that it was sort of, or one of the difficulties was in order to create an index of, it's a million CVs that we're putting in there. It takes like 45 hours.
Really?
Yeah.
A million documents?
Yeah, a million documents, Word documents essentially.
Okay, how big are the documents?
Well, they're CVs, so the German ones are ginormous, and it's a sort of.
Well, I can tell you that the Twitter one, so index creation is basically costs you nothing. It's just an empty index. But when you start indexing into it, I indexed a million things on that EC2 machine. It's a large instance it was doing about 3,500 documents per second.
Okay.
I mean,
fair enough.
And they were probably like half a kilobyte to a kilobyte each, but you know.
Yeah, it sounds like it's performing a bit better than.
Well, it's distributed too, so you can if you do it in such a way that 5 shard index and you have 5 machines, then it will assign a primary shard to each machine, and when it's indexing, all those machines will indexing at once rather than just doing.
And then they'll copy across to each other. So.
Yeah.
Excellent.
Hello, down here.
Yep.
Yeah. So I just wonder whether it had the other sort of Solar type things like spelling suggestions and synonyms. I didn't see them.
I don't think that's in yet, but he definitely has plans to add those because those are available in Solar, I think. So, anybody else? Oh, one more.
Yeah, I had a question whether you had actually tried Solandra.
No, I haven't. I saw that in your talk, and I went to search for it, and there's very few references to it right now.
It's pretty new. Lusandra, which is the previous version based on Lucene.
Okay.
It's quite similar. It doesn't have this nice API. It's using the same API as Solar, but it's backed by a Cassandra cluster.
Yeah.
So
I
it's
haven't
similar
used it.
concept.
I don't know.
So, no, okay.
Sorry.
So you can't compare them. Thanks.
I don't use Cassandra either. So.
Okay, I think we are done in time unless there's some other
Yep.
questions. Okay,
I think that's it.
so thank you.
Thanks a lot.